Okay, our third and final circuit here using linear algebra. Okay, like I had mentioned in part two, this being part three, I was going to make a more simplified circuit, but I was going to show you how this is done with more than one power source. So again, I won't be trying to tackle this problem with the usual way the electrical one and electrical students are taught. And the reason why it is extremely difficult, I'm not going to say impossible, because if it can be done one way mathematically, it can be done several ways. But effectively, realistically, it would be extremely difficult and not at all the way you'd want to tackle a multiple power supply circuit set of calculations. But doing it how I've shown over the previous two videos, you'll actually see just how simple it is. And going back to that first video, just how absolutely robust this methodology is. But again, we don't teach this in electrical 1 and 2 just because it's not the path set out in these particular classes. They don't have the prerequisite math that you need to do it like this, and we don't give you circuits like this. Okay, so let's move on here. You see we've got a 12 volt power supply and a 5 volt power supply. Now it's going to be important that you pay attention to details. So first of all, for simplicity, remember I had mentioned that you can make your arrows for these sub-circuits, these branches, any way you want. How I do them is this is the power supply in what we're calling branch or loop IA. So I'm just going to draw it in conventional current flow for that particular loop. Over here, our 5 volt power supply with this left side here being positive. I'm going to draw that loop circuit that we're calling IB in the direction of conventional current flow for this particular battery. So it's important that I point these out because this is where you will run into problems and you will make mistakes. It's just the nature of how things go. So IA is simply these two resistors, okay, 10 ohms plus 25 ohms multiplied by IA, and that's going to get you that 12 volts. But remember, R2 needs to be treated with, because it is in both branch circuits, with special consideration here. And in this case, it's 25 times IB, of course, but you'll notice it's plus because the current on this R2 is going from top to bottom on IA. It's also going from top to bottom on IB. You have to add that current to it, and it equals that 12 volts. Again, here on loop B, I'm going to start off with IB first. Remember, you don't have to put them in order like that. It just comes down to when you're building these matrices. If you're going to do it that way, you have to keep all your IBs, all your ICs in their respective column. So it's just basically 6 plus 25 plus 4 times IB. Now here again, if they're going the same way in loop IA, they're going the same way in loop IB. So it's plus 25 times IA. And that equals the power supply or the voltage on IB, which is 5 in this case. So you've got a bit of a different look from the previous couple examples I gave you. But still, just straightforward. So you put them into your matrix, R times I equals V. So here you just have to remember all your IAs stack up. So it's 35 plus 25. That will equal 12. And then IB, you have to put your IA first. So it's 25 IAs. That's positive. Plus 35 IBs. And that equals 5 volts. Remember that. You augment this matrix. You put it in augmented form. And then you do your reduced row echelon form. And you come out with your identity matrix on the left. And on the right side of this augmented matrix, you get IA and IB currents. So again, Wolfram alpha, if you plug these guys in, okay, you will come up with these values right here. And you notice this one is negative. I want to make a point of that. So once again, the calculation, you have found the currents through R1. So you found I1, you found I3, you found I4. And I just will make a point of it right now that IB is negative, meaning the current is actually flowing the opposite to the way that I have drawn it. so you can know which way the current's flowing, therefore the polarity on a voltmeter. But before we get there, where I actually show you how that works out, I'm going to give you a diagram for that in a moment. We still have to deal with resistor R2, load R2, 25 ohms. We have to deal with that especially because it is the one load in both loops. And in this case, because the currents are adding, because they're both going in the same direction, here from top to bottom, in conventional current flow, I2 is the sum of IA plus IB. So that is the current through R2, we call that I2, and it is going in the direction of IA. Now again, the direction of IA is this way. We noticed IB is actually flowing the other way from this diagram. So when we're summing a larger positive and a smaller negative, it comes out with a positive, and the IA is the larger current flow. It is flowing in the IA direction. So that's something that you haven't necessarily seen before, but again, just pointing that out because that does matter. Now, once you have I2, you now have all the currents everywhere in the circuit. Since you have all the resistances, it's just V equals I times R. You just use the proper I and the proper R, the proper current and the proper resistance, and you'll get your voltage. Pay attention to your polarity, your positive and negatives, effectively, the direction of current flow, and you will get the proper polarity of your voltage. So V1, very simple. IA, it's a positive number, times 10, a positive number, you get a positive number. V2, all right, so we found our I2 right here. Okay, so it was I2 multiplied, and that was a positive number, multiplied by 25, and you get that 7.05 volts. Now again, because you're going this way, the 7 volts roughly is positive here, negative here. And again, the R1 is positive here, negative here. Now V3 is IB, which is a negative number multiplied by 6, positive number. You get a negative voltage. Now, let me point this out. We had it drawn this way, the current flow, and it was drawing unconventional current flow of this 5 volt power supply right here, this being positive. Now you'll notice this negative 1.25 volts means that if you put a voltmeter across R3, this side of R3 is negative. This side is positive. A little counterintuitive maybe, but this is what it's telling you. It's right there. The same applies for V4. IB, which is a negative number, times a positive number, it's negative 0.8332 volts. Now just let me show you the polarity. On R4, this side of R4 is negative. Now, because it's a negative voltage, it would mean that this side of R4 is positive, this side is negative, and the current is flowing this way. That's the reason why it's a negative. Okay, so now let's move over to some software that you have seen if you're a student of mine, and I will prove this possibly somewhat unintuitive situation out for you. So let's take a moment and go towards that now. Okay, so here we are in Multisim, and I've just made up that exact same diagram here, and I put 4 voltmeters in, and you see this is V1, this would be V2, this is V3, V4. Go back to the previous diagram if you've forgotten. I've got my 5 volt power supply here and my 12 volt power supply here. Now take note of the polarity. So I have these voltmeters in the polarity that is the direction of IA and IB. So you'll notice the calculation of V1 was 4.917. Here's the measurement of V1, and you'll notice this is positive because I have positive on this side, negative on this side of the voltmeter, and it is positive. So that is the correct value, and it's the correct polarity, the correct direction of current flow. Now V2, we had calculated at 7.085. A Multisim here is measuring it at 7.083, and it is a positive number. There again, positive here, negative here. So you'll notice the current flow and thus the polarity is accurate with respect to these two voltmeters. So let's take a look over on branch IB. You see here on the left side of this power supply is our positive of the power supply. I have the positive of voltmeter connected to R3. We're measuring V3 here. I have the positive on the positive side. And you'll notice that it is negative 1.25, 1.25 volts. That's what we had calculated as well, negative, meaning that the positive of R3 is actually on the left, not on the right as shown, because it's showing a negative value. So the current is flowing from left to right. And again, on V4, the voltage across R4, we had it calculated at negative 0.8332, and we have negative 0.8333 repeat. This just happened to be in millivolts here. And you notice I have the positive on this side, the left side of R4, because that is the direction we had the current flowing IB, current flow of branch B. And you'll notice it's telling us, because it's negative, that the positive is over here and the negative is over here. As in current flow on R4 is flowing conventional right to left. So if you didn't believe the calculations, here we are in an electronics simulation program showing you this would be the actual measured values if you were to physically build up this circuit and take all of your measurements. And before we go, I just want to show you a program called MATLAB. It actually stands for Matrix Laboratory. So now students actually have access to MATLAB while you're going to school, and you can find it amongst other apps on the system. So this is my personal copy of MATLAB, and I just thought I would take a moment out to show you how we build these matrices in programs, and then just how simple it is to solve them. Okay, so this is just happens to be a screen capture where I put all of the commands up on the screen where you see it here. So the R matrix, the resistance matrix, in that R times I equals V. We simply type it out like this. This is just a temporary R matrix, and it's just commas, and then when we need to start a new row, it's a semicolon, and these are square brackets. And because I didn't put a semicolon at the end, it will actually print out for you what that is. And it's good to do that, because you can see this is our R matrix if you go back earlier in the video. Now I want to also create the V, the voltage vector, because I know that's what I need to augment onto the end of this R vector. So I created this vector. It's the same way. It only has one column, so it's just a vector as opposed to a matrix. Now to augment the two, you notice here I've got to stick this V matrix on the right side of this R matrix. It's just a simple, this is a temporary augmented matrix, just a variable that I used. You can see it's in the exact same form. I want to put it on the right-hand side, so I don't use a semicolon. I just use commas, temp R, temp V, and I don't put a semicolon at the end, which means it prints out the output. And you can see this is exactly what you want to have, the R matrix and with the V matrix appended on the right-hand side. Now, I called it reduced row echelon format, so you can look on YouTube or anywhere, you can see a definition of what that is, and it's simply written in MATLAB RREF, and you put the matrix that you want in brackets, which is this one, and out comes the answer. You get your identity matrix here, and then you get the answer for your IA and your IB on the right-hand side. So 0.4917, which is what we got, and negative 0.2083, which is also what we got if you put that into Wolfram Alpha. So that's how you would, at least in MATLAB, calculate these types of matrix problems. And that does complete this series on calculating the values of electrical networks.